So basically, what I'll try to, what I was trying to explain you is like, we want to know like, which of these features like theta 2, theta 3, theta 4 or theta 1 are important. So we want to actually play around with these, estimates or the, you can say the model parameters. So we want to see like, as per the problem, how to adjust these model parameters so that we can move to this particular situation where we have a just okay model. So
Hello, sir.
yes, yes,
Sorry to interrupt,
yeah.
but I just wanted to know which group's turn is it today to make the note?
Can you repeat again your question? I was not able to hear you properly.
I actually just wanted to know that which group's turn is it today to make notes?
No, it's still group 2 only.
Group 2. Okay,
Yeah,
thank
yeah,
you, sir.
yeah, yeah. Okay, so in this particular situation where you have this thing, right? So here, we want to play around with this thetas. Like we want to know which of these thetas are important. In this particular example, you will observe that only theta 1 and theta 2 are important, and the other theta 3 and theta 4 are not important, because you yourself can understand from here that if you keep theta 3 and theta 4 also into the consideration for this model, you will see that it will give you a highly overfitting curve which you do not require at all. So we want to see how can we play around with the cost function so that we can come up with some modified value of theta 3 and theta 4 that can help us in simplifying our problem. So if you see here, this is the original cost function that we were already working around, and you can see this is the model which you were estimating. This model is basically the is the model which you are defining for a specific problem, and it will estimate some value y hat, and you know that this y hat has to be subtracted from the actual y to get the square of that. So you all know what this cost function is all about. So we will try to see how we can play around and modify these values of theta 3 and theta 4 so that we can come into this type of situation where we have just okay curve. So let us see that. So right now here I am assuming this model m theta xi to be of this particular this is the particular model which I am taking, and you know that you have this xi, right? So you expanded the feature space which we have already explained you in our last lectures. So what you have done is to incorporate the nonlinearity in the curves, which you can see the curve, the data set is nonlinear. So in order to incorporate nonlinearity, what you have done is you have repeated this feature vector 1 by taking its square, by taking its cube, by taking its fourth power. So this you have done by observing the data itself, and what you have seen is the data is nonlinear. So let us fit a polynomial which is of degree 4 and try to see what kind of results we will get. So what we are doing right now is we are assuming this as our model. So now once we have this model, what we do is we actually modify this original cost function which is given over here. So this is our original cost function, and what we do is we actually add the model parameters theta 4 and theta 3 here, and what we do is we actually multiply it with a very high value of 10 to the power 6, let us say. So if I multiply it with a very high value of 10 to the power 6, and now the new cost function is this one which is given over here, and here you can see this is the original cost function which you already know, and this is the modified cost function with the addition of theta 4 and theta 3. So here you can see I have added these two model parameters also along with the original cost function. And now what we are doing, we are trying to minimize this cost function, and we want to see what value of theta will help us in minimizing this cost function. This is what our objective is. So can anyone tell me, like, if I want to minimize this cost function, what will this cost, what will this do to this particular cost function? So if I want to minimize this, what this minimization will do to theta 4 and theta 3? Can anyone tell me that? Are you able to get my question? Like what I am trying to ask you? I want to minimize this. I want to minimize this.
Please again explain it.
Yeah, I want to minimize it. I want to minimize this loss function, okay? So I want to know that if I want to minimize this loss function, what impact that will create on theta 4 and theta 3? Can anyone tell me that? I want to know the values of theta 4 and theta 3 if I want to minimize this cost function. Can anyone comment on that? Like I do not want to know the exact value of theta 4 and theta 3. Can anyone tell me like whether it will be high or will be very low? Like if I want to minimize this complete loss function. Anyone? See,
It will be low
why it will be low?
because it's in multiplication of 10 to the power 6. So to minimize it, it should be low. If it is a higher value, then we won't be able to minimize the whole.
Right. Good. So basically, this is the complete cost function. And if you see, the objective of this cost function is that we want this particular cost function to be as low as possible. So we want this to be close to 0, let us say. So if we want to make it close to 0, you know that this is a factor which is very high. So this factor, if 10 to the power 6 is multiplied with any value of theta 4, you know it will give you a very large value, right? So in order to make this factor come close to 0, what we will do is what this algorithm will do is it will try to make theta 4 and theta 3 come close to 0. Theta 4 and theta 3 will come close to 0 because what you have done is you have multiplied it with 10 to the power 6. Basically, not specifically 10 to the power 6, you have multiplied it with a very high value. So this is just a number. So basically it depends like how high you want to put it. Like you can put 100 also, and in a particular case 100 will also be very high. So depending upon the situation, it will be high or low. This is just a specific example. So please do not consider this as a benchmark that you have to always put 10 to the power 6. It is just giving you a reference that for a particular data set, 10 to the power 6 is very high. In some of the data sets, even 100 can also be very high. So you have to see that, like which value of that will help you out in making this theta 4 and theta 3 goes to 0. So if your model is this model, you have assumed this model, and what happened is now you have actually modified your cost function like this, and now your theta 4 and theta 3 is becoming 0. Then what will happen to this model? What this model will become? It will become theta 0 plus theta 1 x1i plus theta 2 x1i square. Will it become or not?
Yes, sir.
So what's happening now? It's basically, you know what you are trying. You are actually fitting the curve by using this one. But what happened now? You have modified your cost function. You have penalized it with such a high value of lambda, or you can say it's a constant. So if you are raising it with such a high value, what it is doing is it is actually converting this model implicitly into this model. So in this particular case, if you tweak this value to be very high, what will happen is even if you have used this model to fit this curve, you will get this curve, because this curve is obtained by putting some specific value of lambda that is forcing this value and this value to be 0, as a result of which you will get this curve. Okay, let us say if you do not know which theta you have to tweak, and if you do like this, let us say 10 to the power 6 theta 2 square plus 10 to the power 6 theta 1 square. Let us say if I keep this also, and now if I would try to minimize, what will be the situation now? If I want to minimize this modified cost function again, what will be the value of all thetas? It will all be close to 0 or not? They all will go to close to 0. So if all of them will go to close to 0, how will your new model become? The new model will become theta 0, because you have penalized theta 1, theta 2, theta 3 and theta 4. So all of them you are trying to minimize. So if you are minimizing, then all of these parameters will become close to 0 or equal to 0. It will be like very small, 0.0001. So that is very small, so we can neglect it. So if you penalize all the parameters with a very high value of lambda, then what will happen is you will end up with theta 0. And what is theta 0? Theta 0 is nothing but it's a what will be the equation of theta 0? Can anyone tell the equation of the line? If I plot m theta xi equal to theta 0, what will be this equation? Okay. Okay, so what this situation will lead to is it's a underfitting here, and so what it tries to show you is that if the lambda which you are actually playing around with, if you try to keep that lambda too high, then it might be the case that your curve will end up from here to here in the extreme situations if you keep lambda too high. And if you keep lambda reasonable, then it might be the case that your curve will shift to this curve. So you have to find out the optimal value of lambda, which can move your curve from this particular portion, which is highly overfitting curve, to a normal fitting curve, which is like this. So this factor is called as lambda. This is basically the factor which you are multiplying with all these model parameters is called as lambda, and it is also in short called as regularization parameter. So regularization parameter. So this particular value of 10 to the power 6 is somewhat acting as a regularization parameter, and we call this as lambda, and it helps us in regulating the shape of the curve, as I have shown you through this example. That is, if you make lambda too high, like I have shown you there, right, at 10 to the power 6, what will happen is this type of curve will become like this, a flat curve like this. But if you keep lambda reasonable by tuning it, like you have to experimentally change the value of lambda and see your curve changing. So if you change the lambda by experimentation, then you will see that this curve which is shown over here will change its shape every time you change the value of lambda. And then you have to observe that which value of lambda is suitable for this particular situation where you have a just okay curve. So you have to play around with lambda. So there is no specific value of lambda which I can give you that this is the value, you have to put this and you will get this curve. It's not like that. You have to actually play around with it. You have to experimentally see how you can do it in order to find out the best point where you feel that the curve is just okay curve, or in this situation. So what happens is the actual model will now be 1 over 2m summation I running from 1 to m theta xi square minus yi whole square plus. So what happens is now we are calling the modified function which is over here by this. So what we are doing is we are running from I to 1 to n. Note here that this summation is running till m. This summation will run till n. And note that we do not know which theta we want to keep. Like there are multiple thetas, right? We do not know which theta will be penalized to which extent. So what we do is we take all the thetas into consideration except theta 0. We do not penalize theta 0, but we penalize all the other thetas so that I will be running from 1 to n and it's not running from 0 to n. So this is the modified cost function. So earlier we used to write the loss function as the one which you already know, but now your cost function will become the modified cost function will become this. Summation I running from 1 to n theta I square. So now once we have this modified cost function, let us see what will be the value of the optimal value of theta. So as you know that the expression has changed for the loss function, so this will result in the change in the value of theta also. So here if you see, earlier you had this loss function, so corresponding to that we have already discussed the value of theta which we got last time, and it was x transpose x. So if you have only this particular cost function, in this situation, if you recall, the estimated value of theta was x transpose x inverse x transpose y. So if you recall, you will come to know that we derived this expression for the estimates of theta if this is the only cost function you have. But if you have this particular cost function which is over here, then this value of theta will also be different because your cost function is different now. So what you do is you actually, in order to make this implementation fast, what you do is you normally convert all these, all this equation into a matrix form. So that can be easily represented in the matrix form like this. If you do it, it will be like this. So here this is the norm of a vector, and this we will explain you in the coming slides, but this is nothing but it's basically, it's basically all the, if you have a vector of theta 0, theta 1, theta 2, all that stuff, then what happens is this theta, this is 2 norm of theta, and that is nothing but it's theta transpose theta. So which is nothing but theta I square summation I running from 1 to n, if you write in terms of the individual values of this vector theta. So all these expressions are same. So what I am trying to do is I am trying to represent the matrix version of this expression. So the matrix version of this expression is nothing but it is this here. So once we have this particular expression in our hand, this is the matrix format. And remember that what I have done is actually this 1 by 2m is trivial. So if I multiply this 2m this side, it becomes 2m lambda. And then 2 times 2m lambda, we can take it as another variable which is lambda dash. And that lambda dash we can actually again take it as lambda. So basically this particular constant do not play any effective role in optimization strategies. We can actually move them around, and we can do the change of variables so that you can come up with some different variable here. So 1 by 2m I have multiplied this side, so it's 2m lambda, and 2m lambda I am taking it as lambda prime, and lambda prime is again I am taking it as lambda. So it's just the mathematical way of replacing all these variables. So this is lambda here. Now if I want to so basically what is theta at? Theta at is nothing but its argument that minimizes the value of this expression. So if you differentiate this matrix, what you will get is basically 2x transpose x dot theta minus y plus 2 lambda theta equal to 0. So this is the expression that you will get once you take the differentiation of this loss function with respect to theta. So basically this is a loss function, and you want to take the differentiation of this loss function with respect to theta. So this is the thing that you will get over here. And once you equate it to 0, because you know that you will get the 0 value of you will get the minimum at the 0 location. So once you do that, what value you will get here? You will get theta as x transpose x plus lambda I inverse x transpose y. So this is basically the expression. If you recall, we started out in our earlier lecture, and I told you that just forget this for a while, and we will come back to it later. So now you can see this extra term is coming along with the complete inverse, which is x transpose x. Earlier this was not there, but because of the effect of lambda, it is actually coming inside this expression. Any questions here related to this? So can anyone tell me what is the advantage of using this equation compared to this equation which is over here? Like you have this also, right? we calculated last time, this was the expression, right? So can anyone tell me what is the advantage of this compared to this? Anyone can answer this? Am I connected?
Yes, sir.
Yes, sir.
Okay, so any idea what is the advantage of this expression compared to the one which we had already originally we had? So basically, if you see this particular thing, right, you are taking an inversion of the matrix. So if you are taking inversion of the matrix, what will happen is, let me show you that. So here, if you have this, right, this particular matrix you have, right, x transpose x. Let us say you have this, right. What happens is if you have only this matrix, if you do a eigenvalue decomposition of this, you will get US V transpose. This is the eigenvalue decomposition of this matrix, and where U is the eigenvector matrix and S is basically the eigenvalues matrix. So what happens is, once you decompose this matrix into its eigenvalue decomposition, what happens is this value of eigenvector, which is S is basically the S is basically the matrix of eigenvalues. If you see the structure of this matrix, it will be like this: lambda 1, lambda 2, all this up to lambda, let us say k. So what happens is, these are all eigenvalues of this x transpose x. So all these lambdas are eigenvalues of this x transpose x. So what happens now is, if you invert this matrix, the corresponding eigenvalue decomposition becomes US inverse V transpose. So basically, not V, it's U only, US U transpose. So basically what is happening is, once you invert the matrix, the corresponding eigenvalues matrix also becomes inverted, and if you see the corresponding elements of this matrix, it will be 1 by lambda 1, 1 by lambda 2, and it will be like 1 by lambda k. Okay, so here what happens is, normally in the real data set, when you go for real data set, it might be the case that some of the features may be correlated. So when you do a basis expansion, maybe because of that, some of the features will be correlated, or maybe because of the reality of the data set, some of the features that you have used in the real data set may be correlated with each other. So if the features are correlated with each other, that means some of the columns can be expressed as the linear combination of the other columns, because it will be a correlation between the two. Then and because of that, what will happen is, some of the values lambda k's of the eigenvalue, some of the eigenvalues will be actually 0. Some of the eigenvalues will be 0 because of the correlation among the columns of the matrices. So if this is basically 0, what will happen is, once you take the inversion of this matrix, which is x transpose x inverse, what will happen is, some of these values will become 1 by 0, and this 1 by 0 means it's infinity. So because of this problem, that is, you will have infinity here as one of the elements, what will happen is, this particular matrix is not invertible and it will create problems. So that is the main drawback of this particular cost function which is given over here, that is for real data sets and in which the features are correlated. In this particular situation, this particular matrix is not invertible, and it will result in it will give you infinite value, and because of that, your theta hat estimation will be also corrupted, because it will give you an infinite value of the estimated value of the theta hat. So in order to avoid this situation where your theta hat will blow up, what we do is, we use regularization, which we have included here. So this regularization lambda parameter, you can see now, it actually enters inside this inversion. So if it enters inside this inversion, what will happen is, now your modified matrix is actually x transpose x dot transpose x dot plus lambda I. So this is your modified matrix, and if you do the eigenvalue decomposition of this, it is u s u transpose plus u I u transpose, that is lambda. This is the eigenvalue decomposition of this. So what you can do is you can actually take s plus lambda I u transpose. So this is basically your modified eigenvalue decomposition for this modified matrix. And now if I take inversion of this, what will happen is it will be s plus lambda I inversion u transpose, and the elements of this will be now 1. So elements of this will be actually it will be lambda, sorry, not lambda here. So let us take this as just to avoid confusion, let us take these values of not lambdas, let us take them as c1, c2, c3 like this. So this is 1 by c1, this is 1 by c2, and this is 1 by ck. So now in this particular case, what will be the modified value? Modified value will be c1 plus lambda, c2 plus lambda, c3 plus lambda, it will be like this, and c4 plus lambda, it will be like this, are diagonal values of diagonal eigenvalues. And once you do the inversion, it will be 1 over c1 plus lambda, 1 over c2 plus lambda, 1 over c3 plus lambda, like this. So all the other values are 0 here. So off diagonal elements are all 0. So now you can see in the earlier case, we had this situation where these c values, some of these c values will be 0 because of the correlation among the columns of the vector. So now if that situation happens here, will it go to 0? Will this equation go to 0? Anyone can answer? Can anyone answer that? Will this go to 0? Sorry, will this go to infinity if I put the values of c1, c2, c3 as 0? This is because you have this lambda value along with this, right? So if c3 becomes or c2 becomes or c1 becomes 0, we still have 1 by lambda, 1 by lambda, 1 by lambda as the diagonal elements. So what is happening in total is basically it is this particular regularization lambda is helping us to make this inversion of the matrix stable. So the inversion of the matrix earlier was not stable, it became infinite, but now this infinity situation is resolved if I use regularization as one of the parameters. So here you can see now that with the inclusion of lambda I, we have regularized the solution. So we say that we have actually regularized the solution. We have regularized the solution theta hat by using this lambda as the parameter, which will help us in giving you better estimates of the theta. So this is basically the concept of regularization in machine learning. So why you are using regularization in machine learning? You are using regularization in machine learning by actually this is the basic explanation for that. So if anyone asks you why we want regularization, you can explain it with multiple ways. One of the ways is through this particular stuff. Then another way is through this particular stuff where we have eigenvalue decomposition. So these are the two different ways of explaining the importance of lambda. The third way of explaining the importance of lambda is by showing you this mathematical calculations, which I will show you here. So before going there, so let me tell you one thing. So if the role of lambda, so let me show you the cost function now. So the cost function is what? The cost function is basically x transpose x minus y plus lambda times this thing. So this is the cost function that you have. So there are two extremes, like one is lambda equal to 0, another one is lambda equal to infinity. So in these two extremes, what happens is if your lambda is 0, you can see it from here. If you put lambda is equal to 0, you will get x transpose x minus y square. So basically you are actually going back to the original state, original discussion where we calculated the value of theta hat as theta transpose x dot transpose x inverse X transpose Y. So you will actually go back to your original solution if your lambda is 0. If your lambda is infinity, or you can say it's tending towards infinity, not infinity, then your cost function becomes this. So if your cost function becomes this, and if you want to minimize the value of theta, because you are trying to minimize arg min lambda theta square, so you want to know which value of theta will minimize this. What it will give you is, it will give you a value of theta equal to 0. Theta estimate is equal to 0. So all the values of theta that you have will become 0, because you are actually minimizing this cost function now, as your lambda is very high compared to this first term. So what is happening is, all the estimated values of theta become 0. That means you are getting a curve which looks like this, as I have told you last time in the model fit, because it is penalizing all the values except theta 0. So this particular cost function will give you this particular curve, which is the underfit curve or highly biased curve, which is the straight line like this. So basically what you have to do is, you have to actually be in between the two. You cannot go to infinity. If you go to infinity, you will get underfit curve, and you cannot go to 0 also. If you go to 0, you will be actually going back to the original problem where you have this theta. And we do not want to work on this theta, we want to work on the regularized version of the theta. So you have to be in between the two to get the better estimate of theta. So this is the role of regularization parameter, which we call as lambda. So lambda is nothing but it's a regularization parameter that controls the cost function. So if I want to compare the two different type of things, like two different type of algorithms, which is vanilla algorithm and the ridge regression algorithm. So ridge regression is nothing but theta square. So if I am using this as the norm, then this is also called as L2 regression, or it is also called as ridge regression. So if I am using square of the theta, that is theta 2 here and 2 this side, so L2 norm, this is called as L2 norm, and this is basically ridge regression. And what is vanilla regression? Vanilla regression is nothing but with lambda equal to 0. So if lambda is 0, that regression is called as vanilla regression, which is the original regression which we started out earlier when we discussed that regression in lecture 3 or 4, somewhere like that. So what I am trying to show you here is that if your original samples y are related to the samples x with theta star plus epsilon naught. So what I am trying to do is I am trying to model the data points y from x. So here if you see, we have this original data x stored in this matrix format, and we have the corresponding ground truth theta hat. So we do not know this ground truth theta hat, but let us say we have some actual, we want to estimate this theta hat, which is the ground truth. So we want to estimate these values, and let us say these values are theta star. So if I want to generate y, what I am doing right now here is I am multiplying this data set with the ground truth value theta star, and I am adding noise to it. So if I am adding a noise epsilon naught to this particular matrix vector multiplication, then I am getting some y generated samples. So now we know through vanilla linear regression concept that our theta star, that this is the estimated value, which we are estimating, and that value comes out to be this expression, which we already know from our earlier discussions. So now what I am doing is I am actually putting this value over here, which is over here. So this is the y, right, which is the generated samples. So we are putting that value as this. So once you have this, we can actually cross multiply these terms with this and this with this. So here you can see basically you will get two terms here. One is on the left side, another one is on the right side. And now from here, these terms will, this is basically A inverse A, so its value will be identity. So this will be gone, and you will only left with theta star. So this is the theta star. plus you have this expression which is also there. So now this is another way of telling you that you want this theta star to be equal to you want this theta hat to be equal to theta star, because this is the actual value you have to estimate. This is the actual value you have to estimate, and the estimated expression on the left side tells you that it is theta star plus this expression which is on the left times the noise vector. So you can see here, this is the noise vector. So what is happening now is, if you have noisy observation, you know that this particular inversion is unstable. It can give you a value of infinity also. So if this particular inversion can give you a value of infinity, this infinity, when you multiply it with noise, will corrupt your signal here, will corrupt your estimate the theta value. So this theta estimate, which is the actual one you have to estimate, will be add up with the value of this noise epsilon naught multiplied with a very large value x transpose x inverse. So what will happen is, your theta estimate, which is the estimated value, will get corrupted because it is added by this value. So this is another explanation that why this particular estimate is not good. We are showing you through different explanation. In the earlier one, I have done a eigenvalue decomposition of this matrix, and I have shown you from there that how this is not a stable one. And this is again another way of explaining that if you have noise in the data set, then this noisy observation will get amplified. It will get multiplied with such a high value, which is given over here, that can corrupt the original value theta star, and because of that your estimate will not be a good estimate. So this is the problem with the original one. Let us see how lambda will help us in solving this. So here you can see, if you put the value, so this is nothing but it is basically x transpose x plus lambda I times x transpose y. So this expression we have already derived earlier. So now what I am doing is I am putting the value of y as this one, which is already, we are telling that it's this. So once we have this, you can again separate them into two different parts. And once you have separated them into two different parts, now you can see that your lambda is actually helping us in, first of all, making this inversion stable. And it is, it's now basically, you are getting a regularized version of this theta estimate. You will not get the exact theta star. Please remember, it will be close to the original theta star, but you cannot get the exact values. But it will be regularized by this lambda, which you can see over here. And then this noise also gets reduced by using the proper value of lambda, because now this is not infinite, but it is controlled by this lambda I. And because of this, your noise is controlled. So here your theta star which is the estimate of the theta, is a function of lambda. So as you change lambda, your theta estimate will change, and it will be a function of lambda, but it will be close to theta star, but will not be exactly equal to theta star. And the problem of inversion that you had here in the earlier case will also go away. So it has been shown that if your lambda is basically this expression, it is less than this value. It has been shown that if you select your lambda to be less than this value, then your mean square error that you will get in the estimated value of theta as a function of lambda in the case of regularization is less than the mean square error that you will get in the estimate of the theta if you use this particular expression. So this thing is basically proved in this paper. If you want, you can go into this paper and you can see the derivation. So in that derivation, it has been shown that if your lambda value is restricted in the range less than this value, then your mean square error of the regularized version of the theta estimate is less than the mean square error of the unregularized case of theta hat. Any questions here in this particular description of the regularization? So this is basically the concept of regularization and how regularization plays its role in the case of machine learning. So this is the discussion for that. Let me give you another picture that how regularization is helping us in the optimization, showing you some graphical representation. So here you see, if you have some cost function which looks like this, so these are the cost functions. So what happens is, if your initialization of the algorithm, if it is initialized here, or if it is initialized here, or if it is initialized here, will you all agree that these points will not move if you are using gradient descent, because they are actually at the complete flat curve here, right? So the curve is completely flat. So you know that the derivative of the loss with respect to the theta parameters is 0 in these regions. So these points will not move at all to this side or to this side. So this is basically the problem in the case of non-convex functions. And non-convex functions, please note, I have already told you last time, it will have multiple minimas and it may have a global minima. But in case of convex functions, you will always have a global minima. So basically here it's a non-convex function, but you will have multiple local minimas. So you can see there is one local minima here, but there is one global minima this side. So the problem is, if you initialize your points on these flat curves, it might be the case that your algorithm will not move at all, because the derivative of the loss with respect to theta at these points are all close to 0. So what happens is, once you use lambda, so lambda tries to change the cost function. So if you want to pictorially see that how this lambda is helping us, so what happens is, this lambda, if you move this lambda up or down, what will happen is it will change the quality of this curve. So you can see now the curve becomes slopy at this point, and it becomes slopy at this point, as well as it changes its shape at this point also. So now if your algorithm is initialized at this point, then you will have some gradient coming up here, and because of this gradient, what will happen is your point will actually flow down to this point in this valley. And if your point is initialized here, because of the gradient which is there, it will actually move down and it can fall into this hill. So you can see now that with the value of lambda, if you change the value of lambda, the curve can change, and as a result of which the points can point will move down to the hill and can fall into the local minima. So that is basically the importance of lambda graphically. I'm trying to show you here. Similarly, if you see here, we have these as the saddle points in the curve. So if you see here, if your point is initialized at this point or at this point, then what will happen is your points will not move at all, because gradient at these points are close to 0. So when you try to incorporate lambda, it will change the value of the curve, and because of that, if your point is initialized here now, it will feel some slope, and because of that, it will go back to this local minima here, or a global minima this side. So lambda is basically trying to change the curve, and it will try to make this curve a bit a slopy curve, and because of that your points can go back and can fall into the local minima. Earlier it is not possible. So lambda is helping you in doing this. So this is again another way of explaining that how lambda is helping you in improving the results. Okay, so here I am trying to show you the pictorial representation of these two curves here. So what I am trying to show is the you have this equation, right? X theta minus y square plus lambda theta square. So we are trying to see because you are trying to minimize this loss function. So we want to see that how this loss function, this one and this one looks like in the two-dimensional plane. So if you see this particular loss function, you know the contour plot of this particular loss function I have already discussed in the initials of our course. If you know the contour plots of this will look like ellipse, and you can see it's a red curve which is over here. So this contour plots are the contour plots for this particular loss function. For this particular function which is theta 2 square, we will discuss the properties of this in our next lecture, or maybe today's lecture only. We will see whether we can cover it or not, but the properties of this is easy. This is nothing but it is under root of theta 1 square plus theta 2 square. So this is it will be not under root, it will be square of this. So it is theta 1 square plus theta 2 square. So you can see if it is theta 1 here and theta 2 this side, then this particular loss function, the contour plot of this loss function will look like this, a circle. Because it's an equation of a circle, right? Theta 1 square plus theta 2 square. If it is a, let us say, constant k square, then it is a equation of a circle. So you can see the contour plot of this, which is given by black, is basically the contour plot of this cost function. And this is the ellipse, which is the contour plot of this cost function. So now what we are trying to show here is that how if you want to find the solution of this, the solution of this you know already, it's theta star given by x dot transpose x plus lambda I inverse then x transpose y. This is the solution of this particular cost function. And if you see here, the two curves are actually meeting at this green point. So pictorially, mathematically, when we say that theta estimate is given by this, it means actually this is the point where you will get the solution for the two curves. Because you know that if two curves meet each other at a point, it will give you a solution for the linear system of equations, right? In the similar way, here we are trying to solve this particular loss function graphically. So you can see one graph is this, another graph is this. So the intersection of these two graphs will give you the solution, which is theta estimate. So here you can see now it's a green curve which is giving you theta estimate. Earlier when this was not there, the theta estimate was this point. So this was nothing but, it is nothing but x transpose x plus inverse x transpose y. So earlier this was the estimate of the theta hat. So earlier this was the estimate. Now this estimate has moved to this point, and the movement of this estimate to this point happened because of the regularization parameter lambda, which tries to control these two cost functions separately. So it is trying to actually, lambda is trying to balance between the two curves, which is this one and this one. So this is the point where you will get the value of theta star. So this is again giving you a pictorial representation of the solution that you will get by solving these two equations. Any questions here? Okay, so if you do not have any questions, then up to this point, group 2 will do the assignment. After this, they can stop. So this up to this point, group 2 will write the literature. After this, group 3 will start. So how many of you are in group 3? Can you speak? The people who are in group 3?
Yes, sir.
Okay. Okay, so group 3 will start from here. So this is group 3. Okay, and the deadline for you people will be next Friday. So this is for group 3. And I will tell you when to stop in case of group 3. Group 2 can stop here at this point. Okay, so now what we are doing is we are trying to study various type of norms. So if you recall, in our earlier case, we had taken these things, right? This one. Let me show you that. Yeah. If you recall, I have taken this particular thing, right? Theta 2, 2. This is basically called as norm. And right now we are calling, in this particular case, it is L2 norm. This is L2 norm. right now I think we are, I think time is nearby, so it will be difficult for me to start that new one. So maybe we will try to do it in the next lecture. Yeah, in the next lecture. So right now here this is the L2 norm in this particular case. But now once we try to see what kind of different type of norms we have. So in that we will have different type of norms, which is L2 norm, L1 norm, L0 norm, L infinity norm, and LP norm. We will discuss why we need these norms and what are these different type of norms in our next class. So if you have any questions now related to what I have discussed till now, you can ask me. Otherwise, I will close this class today. Any questions?
No, sir. No.
So are you able to follow what's going on in this particular course?